Hey folks, welcome to this channel and welcome to this video. I'm Saptarshi. I'm a software engineer 3 at Google and a computer programmer. So in this video, I'm going to look at the Codeforces Round 955 Div 2 that happened a few hours back. We had 6 problems over there. So in this video, I'm going to discuss the first 4 problems A, B, C and D. And we'll discuss the solutions in depth. We'll look at the problems, we will go through the approaches, and then I'll take tourist solutions as quick references. We will see few things how he has done, where he differs maybe from my approach. We'll have some analysis over there. There is some reason due to which I have actually liked this contest. After a good amount of time, I'm actually looking at a Codeforces contest, but I like this contest because it has a good mixture of mathematical stuff, uh, data structures and algorithms. It has some versions, some parts actually from all these different, stuff. So yeah, let's look at these problems and let's enjoy solving them. So if you have solved the contest, then this is a quick attempt to come up with an editorial. You can refer to these solution approaches and compare with yours. And if you haven't participated, I would encourage to maybe look at the problems and then think your own approaches and then look at how I'm approaching it and maybe compare it and then let me know in the comments whether you get some fine insights or not. So okay, let's get started. The first problem, but before we proceed, uh, here's our inspiration, Tourist, the legendary grandmaster, whom I've been following from my college time. So something that I like showing young folks and everybody is basically the way he has been consistent over the time. He has risen. He had a very steep curve in this part, but still, what comes up, what really comes forward is his consistency of staying in the sport for more than 12 years. A bright inspiration for many of us. So yeah, and there are many ups and downs over here, but never has he left the sport. So a lot of things to learn over here. Anyway, so let's proceed and see what we can understand from these first 4 problems. Here it says that at some point of time, the scoreboard of some game reads as x is to y or x colon y, and then at a given amount of time, at a given time, instant of time, only one team can score a goal, and then x y would become x plus 1 y or x y plus 1. That is, one of the teams will basically get an increment of one goal. Now the thing is that Dima had actually Dima had looked at the score at one point of time. We are referring to that as x1 y1, and then Dima looked at the score, it had become x2 y2. And what we want to know is it possible that while she was not watching the game, the teams never had an equal score? So essentially, in the problem A, there was a score x1 is to y1, and now it has become x2 is to y2. Definitely x2 is greater than equal to x1, y2 is greater than equal to y1. And we want to know that is it possible that the teams never had an equal score? Is that possible that they never had an equal score? So let's take some examples. 1, 2, 3, 2. If we have 1, 2 and 3, 2, we know that definitely what has come in between is 2 is to 2. So definitely this is unavoidable. They will have an equal score. If they have an equal score, if we cannot avoid an equal score, then the answer is no. If we can always avoid an equal score, for example, if it is possible to avoid an equal score, for example, let's take an yes example, like the third one, 1, 2, 4, 5. 1, 2, 4, 5. It is possible for them to have an equal score. They can both have, between these two instances, they can both have 3, 3. It is possible, but is it possible to not have an equal score? That is also possible. We can have a different transition, something like 1, 3, 1, 4, 1, 5, and and then gradually 2, 2, 5, then 3, 5. So over here, the scores have changed in such a manner that they don't have an equal score. We have to infer this, that is there any possibility that they never had an equal score? If they never had, we will say the answer is yes, that they never had an equal score. There is such a possibility of intermediate results. And if there is no such possibility, then we answer no. If we know that by any means some equal score is guaranteed to come, then we have to answer no. How to solve this problem? So basically, we have some x1, y1, x2, y2, and we are asking, hey, is something like this, x and or something like this, z and z, avoidable or not? When is that unavoidable? So let's say we are going from this guy, the first guy, x guy, is basically going from x1 to x2. Initial score x1, final score x2. And the next guy is basically going from y1 to y2. Over here we know that eventually y will be ahead of, sorry, x will be ahead of y. And they are starting in the same way. X is starting later. So we can say, hey, x can first reach. Let x reach its destination first. And then y can go. Then y can be increased. In that way, what will happen? That basically, x and y will never become equal. They are initially over here. Now we will say, okay, let's take this x and let us move it ahead. Plus 1, plus 1, plus 1, plus 1. Let's move it ahead. Now we can move this y. We can move this y by the plus 1s till the end. In this way, what happens that x is never equal to y. So over here it is possible. In this kind of a curve, it is possible. However, in the case where we found it is not possible, what was that case? Let us think. That if, let's say, x starts here, ends here, and y starts here, ends here, if this is the case, then our x is starting basically at a lower place and will definitely overtake y. It is imperative, it is apparent that x will overtake y. In this case, x at one point of time will overtake y. Will overtake y. In this case, it has to overtake. That could happen here also. It could be possible that y overtook x and then x overtook y to reach x. That was possible, but not compulsory. Here it is compulsory. If x is starting before and reaching later, or basically x is starting at a lower score and reaching a higher score, definitely x is crossing y, and before crossing y, x and y were equal at one point. X equal to y at some point. The same thing holds for the converse, where x started later and y actually started earlier, basically at a lower score, and in reaching the higher score, somewhere y is overtaking x. So here exactly the other situation holds. We know that y will overtake x, and thus x equal to y will happen at some point of time. Now initially it is given that x1 is not equal to y1, x2 is not equal to y2. So this is the important thing to be checked, that we need to check these two conditions. Is one of them overtaking the other or not? So the first condition basically can be checked in something like this, that if y1 is greater than equal to x1 and y2 is less than equal to x2, I think the equality signs can be ignored because we know that x1 is not equal to y1, x2 is not equal to y2. And over here, this is the other case, which is x1 is greater than equal to y1 and x2 is less than equal to y2, which means that the relationship between the lower x and lower y and higher x and higher y are opposite. We can infer it in this way, that the relationship the relation between x1 y1 is opposite to that of x2 y2. So in that case, it is definitely going to overtake. So the answer is no. The answer comes out to be no over here, that we cannot avoid the the clash, the collision. So then the other case is basically, if this is not the case, basically if both are both x and y have the same relationship, like x1 has the same relationship with y1 as x2 has with y2, then the answer comes out to be yes. That is the idea. If you take some examples like this last one, you can see x1 is greater than y1, but x2 is also greater than y2. So it's the same relationship. Same relationship basically tells yes, they don't need to overtake. None of them needs to overtake the other. It is not compulsory. Over here, it is 1, 2, it is 1, 2, so basically they remained the same. Initially, x was behind, later on also x is behind, so it remained the same, no need to overtake, same relationship. However, 1, 2, 4, 3. So initially x was behind, later x was ahead. So there's a change in relationship, the switch in the relationship. This is what we try to detect and term as no. When you reach this clarity that basically these two need to behave differently, you can write this as something like x1 less than y1 and x2 less than y2. You can actually have equal to sign anywhere. The x1 equal to y1 never happens, x2 equal to y2 never happens, so this is safe. So if I think basically it can be looked at as whether they have the same thing or not. So you can do a XOR kind of a thing. If the results are safe, or you can basically check for the equality, not the AND, the equality. If both have the same relationship, that means yes, otherwise else no. This is the idea of solving this problem. Now let us look at how Tourist has actually solved it. It's basically the same thing. So he has actually implemented the one-liner. Instead of going that roundabout way, that relationship between that one and this one and that one and this one. So basically this is one case, this is the other case. Instead of doing case 1, case 2, he wrote in the simplest way, that are both the conditions same or not. So this is the actually the shortest way of actually representing that. So definitely, we have seen this earlier in my previous videos also. I showed you that in simple things, he has a different knack of implementing them in the easiest possible way, in the simplest possible way. In 1 minute, how something can be done, I think is the best example. So yeah, that's about the first problem. And what I have pointed out before as well is that unlike many other people, he doesn't use very large templates. From his code, you can actually see they are very small in size. His codes are very small in size. He writes exactly what is needed. And that makes him different from many other people actually. Okay, let's look at the next problem, problem B. Problem B is a slightly mathematical problem. It says that we have some variable x and a constant y, and then this operation we have to perform k times, increase x by 1, and while the number x is divisible by y, divided by y. So let's take this example, x equal to 16, 3 and 2. X equal to 16, y equal to 3, k equal to 2. So basically it says in each step, the first step let's say, and k tells how many steps, so there are 2 steps. First step, what happens? X plus 1, so 16 plus 1 gives 17. Then you divide 17 by y as long as it is divisible. 17 modulus 3 is not equal to 0, so we won't divide. So 17 remains. This is the new k, new x. Then the second step, we do this once again. 17 plus 1 equals to 18. And then we divide by 3 if it is divisible. So yes, 18 by 3 gives us 6. Again, 6 by 3 gives us 2. As long as it is divisible, we have to keep on dividing. It gives us 2. So this is x eventually. So we have to tell the value of x that remains after k iterations. So if it would have been just the, instead of k, if it would have been like do it infinitely, do it infinite number of times as long as it doesn't come under uh, 3 or under y. Since we are dividing by y, the question could have been, hey, when it comes to be less than y, then stop the process. Then that would have been a rather straightforward kind of a thing. We would have said that, hey, this x basically will lie between some power of 3 and some bigger power of 3. Or we can say x plus 1 will lie somewhere over here. It will lie in some power of 3, and that power of 3, or sorry, that power of y we have to keep in mind. So my approach would be something like that, find out which power of 3. For example, for 16 we know that 16 is between these two things, 3 squared, that is 9, and 27. It is in this range. So I would say, okay, then 16 basically, closer to 16, which multiple of 9 is present. So after 16, I know 9 into 2 is present. This can be easily found out. We can say something like this, x plus 1 divided by y to the power L plus 1. That tells us basically about this thing, that what is that next number by which you can multiply. So by that I would have found it out, and then that would give me the answer. Basically 9 into 2, so I know that finally 2 is going to remain, something like that. So that is usually going to work if we are allowed to do it not for k steps but for infinite steps. So then I would use something like, I can use something like binary search. I can do a lot of things there. But the trick comes that, okay, it is given that how many steps have to be used. So every plus 1 needs to be kept in mind. Every plus 1, every division, everything needs to be kept in mind. So here I would actually start looking at it in steps. That when does the first division happen? So I will look at it in this way. First of all, x and k go up to 10 to the power 9, y also goes up to 10 to the power 9, but y starts from 2, which means if you divide by y, it will decrease. So x and k range from 1 to 10 to the power 9, and y ranges from 2 to 10 to the power 9. And here starts the process. I will take x and before it reaches any multiple of y, it is simple addition. So I'll just find out, hey, what is going to be your nearest multiple of y? That many times, like let's say that nearest multiple. How to find out that nearest multiple? We can do something like this: x by y, and then plus 1 multiplied by y. Let's call that something. Let's call that as fx. So we can basically say that if fx is less than equal to k, then if fx is less than equal to k, that means we have sufficient moves to reach fx, and that means we will reach fx and then it will undergo the division as well. So then we will basically do something like this, that okay, x will then become fx divided by y to the power whatever maximum, such that y to the power max is the maximum power of y that divides fx. We will reach there and we will say, okay, from k, that many parts are gone. So k minus is equal to that many attempts, which is fx minus x. So from x to fx, we just had to do plus 1, and then we reached fx, and then the division happens. So this is how I'll rush to that point where the division happens. What if fx is greater than k? If fx is greater than k, then I would say okay, then only x plus is equal to k, and this becomes the answer. So whatever x you get, this is the answer. Whatever final x you get, no division by y happens. But if fx is less than equal to k, then the division happens. We will do that division, and then this is the first step. Again with this new x, I'll again do this process. So after this process, I'll take this x and this k, and I'll again do this process. I'll keep on doing this up to a point when x is less than y. Why will I do this up to this point? Because uh, look at this. Whenever I'm dividing this by y, I know that the value is decreasing. The value is decreasing significantly. So let's say I'm at something like 70. So from 70 it will go to 72. Let's say y is 3. So 72 by 3 or 3 square, and then it gets reduced to 8. And then from 8 again, from 8 it goes to 9, and 9 by 3 will again bring it to 3, which means things are reducing. So I'm always reducing this x. So x is close to a certain power of y, and I'm bringing it down to the previous power. That is the achievement. So so far so good. Each iteration like this, each iteration like this, if I talk about this one step, basically uh, we can do this in big O one time, we can do this in big O one time. This is big O one time complexity, each step, and this will happen maximum log n times. After log n times, x will become less than y, because we are basically dividing by y. So basically after log y times uh, log of x to the base y, log of x to the base y, which is, we can say, even if y is very small like 2, it will be less than equal to 30 or 35. So after these many steps, x is less than y. And then what happens? When x is less than y, what will happen? Let's say y is something like 7 and x is something like 5. What happens? From 5 it increases to 6, from 6 to 7. When it increases to 7, it comes down to 1. From 1 again plus 1, 2, 3, 4, dot dot dot, and again up to 7, 6, and then 7 by 7, that is 1. In this way the process continues, and I should not keep on doing this because it's a time taking process. If I see they are all in the powers of 10 to the power 9, I should be very wise about this time. And if you see, there are 10 to the power 4 test cases. So we are not allowed to really go very much polynomially over there. So okay, so over here I will try to optimize. It is it is clear what kind of pattern it is following. If you see, this is the pattern it is following. We are starting from x at this stage when x is less than y. We are starting from x, then x plus 1, then x plus 2, dot dot dot. We are going up to y minus 1, and after y we are coming back to 1, because y and then y divided by y is 1, 1, then 2, and then dot dot dot, finally at x. This is the cycle that is forming, and this cycle is going to keep on continuing. So I have to find out, hey, after remaining k steps, where will I be in this cycle? That is what we need to find out. So there are many ways to do this. If you see, we are basically in this range 1 to y minus 1. For ease, you can basically think this as from 0 to y minus 2. Just a translation, later on we can do the plus 1. So we are reducing by 1 so that it comes in the 0 range, you can apply the modulus. This basically tells us we can apply the modulus by y minus 1. So we can just take it forward and apply the modulus. So basically we can say, hey, currently the value is x. Let's call that x minus 1 because we are translating. And then x minus 1, we can basically say add k to it. Add k to it. And then where will we be in this modular world? We have to basically find out a modulus by y minus 1. to find out where we are in this modular world, and over there we can say let's add the 1 at the end so that it reaches the original, the intended range. So what is this k over here? The remaining k after the previous log of x to the base y steps. After these steps, whatever is the remaining k, that is this k, and this x is also whatever is remaining after those steps. So yeah, that's essentially how this problem can be solved. So we can quickly look at how Tourist has solved this problem. And now you can see how much time he has taken to solve this problem. Just 2 minutes. We have been discussing for so much time. He just took 2 minutes to complete solving this problem from reading the problem. Let us see what he has done. Yeah. So it's x, y, k. He is first checking whether k is greater than 0 and x is greater than 1. This is also a fine strategy that he is taking x up to some point of time. Let us try to understand this. While k is greater than 0, definitely, so that's an important check that something is remaining, and x is greater than 1. If x becomes equal to 1, let us see what he is doing. Then he is basically doing that step, that k modulus y minus 1 plus 1. Here he knows that x is equal to 1, so the thing became simple. Basically, think over here he is checking that x is greater than 1 or not. So over here he is asserting that x is equal to 1. If x is equal to 1, then put x equal to 1 in this formula. 1 minus 1 becomes 0 over here. So this part goes away. Then it just remains k modulus y minus 1 plus 1. Let us see. K modulus y minus 1 plus 1. So yeah. So before that he has done something, maybe something like this. While x modulus y is equal to 0. Okay, let's read this maybe. Int rm equals to x modulus y. He's checking that modulo y where it is currently. So somewhere rm will tell how many steps to go to reach a multiple of y. Rm is less than y minus 1. Then they will add it and k will minus it basically. And how much should take? Basically the minimum. So he's taking y minus 1 minus rm and k. This is the maximum that it can take to reach a multiple of y. To reach a multiple of y, this is the maximum it can take. Why this minus 1? Because he knows that x will become x plus 1. That is why he's doing the minus 1. And then he's checking whether we have the quota or not. K is basically that quota. We have sufficient quota or not to reach over there. Then we do plus equals to take, minus equals to take, and then continue. X plus equals to 1. He increased the value of x to where it should be. And then the division happens. So at least one division will happen, we know that. And then k minus equals to 1, that's also fine, because due to this final division, yeah, let me see, let me check. Yeah, so for reaching, for going actually y minus 1 minus rm steps, it takes this much, and for that extra one step he's doing it separately. That's also fine. Like he's considering only how many steps only addition will happen. He's first looking at that. That okay, that division by y, let us take that later. But how many times only addition is going to happen? He's counting that. That is the take. That is why this minus 1. So before reaching y, a multiple of y, he's checking okay, y minus 1. Up to reaching there, how many steps? He's doing that addition, and then he's doing this extra step. Yeah. And if rm is less than, okay, so this is the case where the remaining thing is less than y minus 1. in which case he is continuing. Anyway, I have a hunch that his code will reach here and then again come down with the same value of x, which is always fine. But he is doing an extra checking that x is greater than 1 or not. Maybe that's why he is continuing. So if it is insufficient, or if x is no longer greater than 1, for those two cases he is continuing it, which is fine. And then this is the part where the division happens, and outside he is doing the same thing that we have done. So essentially, yeah, the steps of his code, the steps of his thinking has been slightly different, but the logic was mostly the same, as you see. So again, the disclaimer that I like giving in these videos is no comparison. He's a great coder, and we are just trying to learn something about these approaches and then trying to tally with these great programmers how they do these things. So yeah, what appears to me is it's mostly the same with few steps different. The way he has thought through the things, the sequence was different. Again, he didn't have the luxury to really sit and think the way we have thought over here. Otherwise, maybe a few things he would have done differently, I believe. But anyway, so yeah, I think this was a good problem. It actually was challenging. Up to some point of time, you would think whether some solution is possible or not, how actually to approach this, etc. And then you have to take the courage. Okay, let me take it to the division point of time. I think that was the main important step over here. Step to that division point. Till then, do that addition or speed that addition, because the 10 to the power 9 was a difficult thing to handle. And now let's talk about the time complexity. So here it was log of x up to here. So basically up to here, it took log of x steps. And this one, this is just a single step. This is just one step. This is just a single step. So we can say the total number of steps is log of x to the base y plus 1. And hence, this is somewhere around 35 plus 1, that is 36. Or we can say overall it's less than equal to 35, should be. Which means your total time complexity, total time taken is less than equal to 35 into t. T is the number of test cases, which is around 10 to the power 4, I think. So this will definitely pass in the time limit because it's less than equal to 10 to the power 8. Okay, so now let's look at the next problems. Problem C, boring day. It basically says that Igor has a deck of n cards. Ith card from the top has a number AI written on it. Igor wants to play a certain number of cards until the cards run out. In each round, he takes a non-zero number of cards from the top and finishes the round. If the sum of the numbers on the cards is between L and R, the round is won, otherwise it is lost. He wants to maximize the number of rounds he can win. So if we take one example, like 2, 1, 11, 3, 7, 3 to 10, 2, 1, 11, 3, 7, from the top or bottom, wherever he is picking, doesn't matter. From 3 to 10, if his sum lies in this range from 3 to 10, then he will win that round, otherwise lose that round. He can choose in many ways. He can say, I will choose these two, then I'll choose these two, then I'll choose this one. Then this one is 3, which is a win, because it lies in that range. So 2, 1 is a win. 11, 3 makes 14. 14 is outside the range, so this is a loss. And 7 is a win. So 2 wins are possible. Let's see if more wins are possible or not. 2, 1, 3, 7. No. 2 wins are only possible in whichever way we think. So there are many ways of grouping. And there can be any number of losses. And the wins need not be consecutive. Those things are given. So here the answer, let's see whether it's okay. The answer is 3. Let us see. First round, top 2 cards, 2 and 1. Oh, okay. 3 and 7. So the better way is basically take 2 and 1, then take 3, and then take 7. So basically he wins 3 rounds. These 3 rounds in these rectangles that I've drawn are his victories. So how can he maximize that? What he is choosing in between doesn't matter. He can choose any number of, he can deselect, he can ignore any number of things in between. Ignoring basically means he'll pick them up. They will not give him any points. He doesn't care. So how many such rounds he can win? So this is a standard DP problem. So I've been currently covering a DP problem set from CSES. That's a very good material for learning DP. You can refer to that. I've pasted the link in the description and over here. So you can look at how we use different DP approaches to solve various problems. This is a straightforward DP kind of a problem. The AIs are very large elements, and the L and R are also large, from 1 to 10 to the power 9. And the N is also large, up to 2 into 10 to the power 5, which means simple polynomial approach, quadratic approach is not going to work. We need something different. So there is a very similar algorithm on this, slightly similar to what is required over here. That is LIS, longest increasing subsequence, with binary search. There are some differences, but it's in some ways related over here. LIS stands for longest increasing subsequence, and we use binary search over there. Okay, so over here, how to solve this problem? After some experience, you can look at this problem and say somewhere DP is involved. Even if you deny from the theoretical version, somewhere the sub-problems thing is involved. And then you can argue whether there are overlapping sub-problems or not. We will leave that theory away. We will just solve this problem. So how can this problem be solved? One thing is, when I'm at one place, I want to decide, okay, up to here, what what is my answer? What is the maximum number of wins possible? Will it help me when I go to the next index? It can, it may not. When I go to the next index, like I can say, okay, what is the answer up to here? Plus a single answer. Or I can say, okay, no, I want to combine this with few elements. And then I want to know what is the answer before. The idea somewhere leads me to the same place, that, okay, if I want to find out what is the answer for this whole array that is up to here, what is the answer? What is the number of wins? Can I say that whatever is the number of wins up to here, if I have that, win 1, win 2, win 3, I can say one possibility is that I'll take the W1 wins up to here. W1 is the number of wins up to here. I'll take W1 wins up to there. And whatever is possible from my last element, that is AR n minus 1, whatever is possible. If it is a win, very good, otherwise it is a loss. I can say W2 plus whatever is possible from n minus 2, n minus 1. I can say W3 is up to here, I will take whatever is the answer, and then I will take these three elements, whatever is possible. ARR from n minus 3 to n minus 1, and so on. So somewhere, this is one way of looking at sub-problems. So I can say that answer at n minus 1 is equal to the maximum of the best answer up to any I plus if I plus 1 dot 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 n minus 1, if this thing basically gives me a win or not. If this is a win, I will take a 1, otherwise I'll take a 0, something like that. So I will do this for all possible I from 0 to n minus 2. So this is one kind of a recurrence. I basically say solve this problem for previous values of I, and then we can solve it here. So you can look at, I had shared a basic video on DP where I had discussed how these problems are approached, how to look at subproblems. I had discussed recursion also in depth in that video. So you can look at that video and then you'll be able to understand recurrences better. So thing is, what do I need? When I say I need answer I, what do I need? That hey, I am taking elements after I into myself. So before, that is up to I, what is the best thing? After I am taking it. So up to I, what is the best thing? That is what I want to know. I don't want that ith element to be included in a win. I don't have that requirement. We have that requirement in LIS binary search or similar problems. Here I don't have that requirement. So I can say, hey, answer I can be, what is the best answer up to I? I may be involved, may not be involved. And that leads me to a DP state. The DP state basically is DPI is basically the maximum wins in array 0 to I. Over here in this range, what is the maximum number of wins? And then it is basically the maximum of DP I minus 1. That is a possibility. If DP I minus 1 including, if ith element does nothing good, then DP I minus 1 will give me the best solution. So I'll take the maximum with another thing. What is that? I'll find out the J. I'll find the J such that what can be a better thing? A better thing can be DP I minus 1 plus 1. It cannot be anything far better, right? Because DP I minus 1 is definitely the best maximum number of wins up to I minus 1. So now DPI can be what? DPJ plus 1 win. Now that DPJ will definitely be less than equal to DPI. I know that. So whatever, so my DPI can actually look like this. If this is I, then my DPI can look like this. I can say, okay, pick up some DPJ and then I will take this part within I. Now DPJ, the maximum it can go is up to DPI minus 1. The way we are configuring the DP is the maximum number of wins in AR of 0 to I. So basically, if you see, if number of array elements increases, if I add an extra array element at the end, the answer will never decrease. The answer will either remain the same or it will increase. So it's a monotonic kind of a thing. The TP values will increase from left to right. So that is the idea. Since we are doing the maximum with the previous value, it has to increase. So I know that whatever dpj, that is definitely less than equal to dp I minus 1. So my profit is if dpj is equal to dp I minus 1. So I will say such that dpj is equal to dp I minus 1 and the sum from j plus 1 to I is going to lie in this range L to I. I want some j like this. Then I can get a benefit. Then I can get dp I minus 1 plus 1 or dpj plus 1. So I have to find such a j. Now, how can I express this? What is the way to express this sum of a range? A very common thing. Sum of a range, sum of any arbitrary range, whenever you have to find, prefix sum comes to the rescue. You can call it as PF prefix sum of I minus prefix sum of j. Yeah. So now, PFI minus PFJ has to lie in that range. That means PFJ will have to be in this range, something like this. PFI minus R to PFI minus L. So the PFJ, the prefix sum of j, has to lie in this range. And so if I know the prefix sums, how to know the prefix sums? It's present. The elements are positive, so the prefix sums are present. So I know from where to where this particular dp I minus 1 value has been coming. I need this kind of a thing. So I can look at that array and I can say, okay, like this, 2, 1, 11, 3, 7. I can look at this, I can say, hey, the prefix sums are 2, 3, 14, 17, 24. These are the prefix sums. And then I can look at them and say, hey, for let's say 24, your PFJ, your previous prefix sum has to lie between 24 minus, so the L and R are 3 and 10. So 24 minus 10 to 24 minus 24 minus 3. 24 minus 3, which is 14 to 21. And so basically this is the range we will allow, 14 to 21. We can find out through binary search that what is the last element in this range, because last element means that much we are keeping for previous wins. So up to 21, which is the last element? 17. So from 14 to 21, these two are possible. We are taking the last element over here. Last element means now, before that, whatever wins were there, we can allow that. So basically up to there, we can take PFI minus PFJ. So yeah, up to J, I'll basically say whatever is your wins. That's what we are doing. PFI minus PFJ and then DPJ. DPJ we will basically consider. So what is DPJ over here? DPJ is, if I take the DP values, up to here it is, 0, here it will be 1, here it will be the same 1, here it will be 2. So we will take this DP value 2 and 2 plus 1 we will do over here to bring 3. So this will take us to over here. So if this is satisfied, if we find, that is the main part, if found, then it will be dp of j plus 1 or dp of I minus 1 plus 1. You can do either. I can leave it as dp of j plus 1. So it will be the max of, if nothing like that is found, it is dp of I minus 1 only. If something is found and if this condition is sort of met, then it will be a better answer, which is plus 1. So in this way you can see here we are getting a plus 1. Similarly here we'll get something like a plus 1, because 17 minus 14 will give us 3, which belongs to that range. So yeah, that is how this problem can be solved using DP. This is the DP recurrence. So we had discussed some previous problem also in a previous contest. We had a similar problem and tourists had solved it in a similar way. Tourist had actually used, similar to over there, a segment tree. He has used a segment tree and a set. So it basically keeps that ordering. Instead of doing a binary search, I think binary search is pretty simple. If you have the prefix sums present, then you can just do a simple binary search and get going. What he has used is, he has used a segment tree, which does basically the same thing. It tells you that which is the nearest element to be taken, and pretty much he is finding the same answer that we are finding through this approach. So whichever way you want to find, it's totally fine, because the answer is monotonic. The DP value will never keep decreasing after a point of time, because we are doing this maximum with the previous value. So I don't see any issue with either approach. You can use any of the approaches. So segment trees is not needed, but I think, again, as I said in the previous video, that he might have done it because he has found this implementation easier. To him, this is the easiest way to solve. That's why he has done it. So yeah, but you can see he has computed the prefix sum over here, and based on the prefix sum, see the same ranges he has applied from pref I minus R to pref I minus L. He has applied the same ranges and found out the values from 2, dpi and see, he is doing the maximization with dpi minus 1, the same as we have done, and then he is squaring, and whatever he is getting, dot mx plus 1. This mx is basically finding out the maximum dp value. So using the segment tree, my hunch is he is finding out the maximum dp value. So his segment tree actually stores the maximum dp value in a certain range. Can be done. Definitely there are multiple ways of solving different problems. This is one way. So, but I think over here he has not exploited the monotonicity of the dp array. His array is also monotonic, but anyway, the definitely it's not wrong, but I think his data structure has more information or more characteristics than what he has utilized. But anyway, uh, definitely we have to look at how much time he has taken to code. He has coded it in 3 minutes. From 3 minutes to 6 minutes he had coded it. So that's insane. Once again. So yes, we are done with the third problem of this contest. I hope you liked this application of dynamic programming and binary search and also segment trees. The last problem is on a 2D matrix. In my opinion, a slightly easier problem. For some moment I was worrying why there were less submissions over here, but I think there were pretty decent submissions by the end. So this was just about holding nerves. It basically says that so there is a 2D array, and then each cell contains a non-negative integer representing the height of the mountain. And the mountains come in two types, with snowy caps and without snowy caps. And we want the sum of the heights of the mountains with snowy caps to be equal to the sum of the heights of the mountains without them. We don't want those exact things to match, like the heights to match. We want the sum of heights to match, sum of heights of snowy and sum of heights of non-snowy. How are the snowy, non-snowy given? Through this line. The zeros and ones will indicate who is snowy, who is non-snowy. Okay. And the initial heights are given. Now you can change the heights. You want the sum to be equal, so you can change the heights, but there is a particular way of changing. You can take a submatrix of size k into k and then add any integer constant to the heights of the mountains within this area. The type of the mountain remains unchanged, which means if it was snowy, it remains snowy. If it was non-snowy, it remains non-snowy. You can choose a submatrix of size k cross k. It's a square submatrix, square part of that matrix of this particular size. K is given, and then you can increase or decrease. So c can be negative. So you can increase the height of each mountain by c, increase or decrease the height of any mountain. I mean, basically all the mountains by the same thing. You can increase or decrease. So then can you reach the same sum? So for this kind of a problem, you should look at what do we want to change. So let's look over here. Problem at hand is you have a matrix where there would be heights 3, 5, 1, 4 and so on, dot dot dot, and then some k will be given. Let's say k equal to 3. That means you can choose any k cross 3, k cross k matrix like this and increase all of them by 1, increasing, or let's say increase all of them by 3. That means this will become 6, this becomes 8, this becomes 4 and so on. Here also the same thing, everywhere plus 3. You can do the same thing elsewhere. You can basically, so you can keep on doing this. This is given that you can do this any number of times. That is given. So before making if it is possible or if it is impossible, as follows: type of mountain, transform. Yeah, so basically I don't find it now, but basically any number of times you can do the transformations. So you can do this transformation, then you can choose another submatrix like this submatrix and do another transformation. Then you can choose another submatrix like this and you can do another transformation and so on. So in this way you can do multiple transformations in the 2D array. And then finally the sum has to be the same. So what is this sum thing? That snowy, non-snowy thing is there. That's like a constant thing. So you can basically find out your sum 1, sum 2. Initially sum 1 and sum 2 may not be the same. Let's say we find out the difference. Let's say the difference is k. You have to bring this k to 0, which means you decrease this one or increase this one. Up to you. Or do both of them. Some combination of both. But basically by chance you have to reach it to 0. How to control it? And it has not been asked what transformations you'll apply. They have asked you is it possible or not. So when you apply, let's say in this green square, let's say you apply plus c1. What does happen? What happens in this case? There are some values, there are some non-values. So basically there are some snowy values. Let's say the snowy sum is s1 and the non-snowy sum is n1. So the sum will change to, when I do c1, the sum will change to s1 plus c1 into the count of snowy, and over there n1 will change to n1 plus the count of non-snowy, c1 into the count of non-snowy. So this s1 and n1 are remaining the same. Those factors are getting added for all the transformations. So for each transformation, if you look at each transformation can basically add some c into the snowy sum minus non-snowy sum in a submatrix. C into anything. So for different submatrices, this value will be different. The snowy sum minus the non-snowy sum, this value will be different. So what does this yes no thing basically mean? Let's say this snowy minus non-snowy everywhere is 0. So in every submatrix, your number of snowy mountains is equal to number of non-snowy mountains. So whatever you increase, increases for everything. Whatever you decrease, decreases for everything. And the net difference comes out to be 0. This is the net difference. So if this is equal to 0, the entire thing becomes 0. So then this has no outcome. This will not help you. Also, there is another aspect. So that is one case where it is not possible, which means if in each submatrix your snowy is equal to non-snowy, then no submatrix change will give any transformation, any net transformation. You need a net transformation. What is your net requirement? This. You need to meet this difference. You need to meet this difference. So your transformation in one submatrix plus your transformation in another submatrix plus your transformation in other submatrices should become equal to your delta sum 1 minus sum 2. And they all depend on what is their current snowy minus non-snowy count. This will be some C1 into delta count in that submatrix, count in M1. This will be some C2 into delta count in M2, and so on, the same thing. Then the question is, this C1, C2 is in our control. So how can we get this sum? Let us call it as delta sum. How is this possible? When is this possible? Let me write down count M1, count M2, and so on. Count ML. In this way, we have the summations. So we have something like this. Some constant C1 into that, C2 into that, CL into that is equal to, we need delta sum. The pink things are given. The pink things are given, the brown things are not given. And you have been asked, is it possible with not, or not? With any brown things, is it possible or not? The pink things are given, the brown things are not given. This is essentially asking this question, hey, is this possible or not? Summation of Ci xi, or let's keep it like this. Is this possible or not? C1 into something that is known, some known value, that is n1, plus C2 into n2 plus dot 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 Cl into nl is equal to n. Does some linear combination of ni's give you n? Is n, can you form n? Can you form n by a linear combination of ni's? Answer is I mean, the answer logically can be inferred that if all the ni's have some common factor which is not a factor of n, then it is never possible. Otherwise it is possible. It is always possible to create n from some ni's. But if ni's, let's say all are even, let's say all the ni's are even, n1, n2, nl, all are even, and n is odd, then it is never possible, right? Similarly, if all the ni's are divisible by 100 and n is not divisible by 100, it is not possible. But if there is no such factor, which means the GCD of all these ni's divides n, this basically gets answered by this information that if n modulus GCD of n1, n2 dot 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 nl, if the GCD is equal to 0, let me think. Yes, so n is divisible by the GCD. It's not that the GCD is 2 and n is not divisible by that. If n is divisible by the GCD, that means it is possible. If true, then the answer is yes. If false, then the answer is no. So you basically need to find these counts in each submatrix. What is the count of snowy minus non-snowy, or the minus of that? What is that count? And then you need to find their GCD and see if n is divisible by that or not. That's it. So you have to apply some mathematics over here to compute this snowy minus non-snowy sum for every submatrix. For every submatrix you need that. For that you can look at every submatrix in the form of +1 -1. +1 means snowy, -1 means non-snowy. For example, if you take this 1 0 0 0 1 0 0 0 0. So you can look at this as 1 0 0 0 1 0 0 0 0. You can store it. You can store it in a matrix like this: 1 -1 -1 -1 1 -1 -1 -1 -1. And let's say k is 2. Let's say k is 2. Then for each 2 you can find out the sum. Now how to find out the sum of all these submatrices? How many such submatrices are there? It can go up to n into m. So we have some hint given that the n into m cannot cross this, so that is a good thing. So you can take n into m time. How to find out? Basically you find out 1, or one thing you can do is up to everyone. So basically you can find out the sum of ij, which will store that up to ij, from the top left corner to the bottom right corner, sorry, basically if this is your matrix, this is your ij, I and j, this is your cell, and we are basically saying, okay, the sum of this thing, that is up to the ith row and up to the jth column, this sum, this entire sum up to this ij cell, this entire sum will be stored over here. Sum ij is equal to that sum, the sum of all the elements in that range. So we can do this. We can again do this by recurrences. We can say, if we have solved for previous values of I and j, we can say sum of ij is equal to sum of I minus 1j plus sum of ij minus 1. In this way, top part is done, and then this left part is done. So this part is done twice. I'll remove it. So I'll remove sum of I minus 1 j minus 1 because I have taken that twice. You'll have base cases for I equal to 0, j equal to 0 if you have. So otherwise this is the recurrence. So we'll have sum of ij, and then using this, if you want to form something like what is the sum of the submatrix for, I mean, ending at ij and of size k cross k, then that thing can be expressed as sum of ij. So think in this way, you have ij over here, ij, and you have something like this. K length, so basically k length, k breadth, something like that. And then sum of ij, this is sum of ij, minus, we can say that you can subtract the sum up to here, and then we can also subtract the sum up to here, and then add this part which we have subtracted twice. So sum ij minus sum, this thing is I minus k, so I minus k j minus sum I j minus k plus sum of I minus k j minus k. So using this formula, you can calculate the sum ijk for all the ij, which is m into n kind of a thing. So all these you can calculate in m into n, and using this you can calculate all of these in m into n. K is constant, that is given. So based on that, you have all the sum ij. Now basically take all of them, take each of these. These are your CIs, or what I wrote above as NIs. These are your delta sums, delta sum i's, and you have to see what their GCDs are. GCD of all the delta sum i's. If they divide, if this divides the required sum, then fine. The required sum can be 0, can be anything. 0 is divisible by all of these, so yeah, that is the idea. And if the GCD comes out to be 0, which means that all of the elements are 0, that only means, so yeah. Then if the actual sum is non-zero, then it won't be the answer. So yeah, those are some corner cases, you can take a look at them. So let us look at what Tourist Sir has done here. In 10 minutes he actually did this. What we actually derived, the things we discussed, he did it in 10 minutes. So yes, he is adding the differences Aij. So he is considering the Aij's as positive if they were 1, otherwise negative, and in that way he is getting the difference. So he is adding the snowy ones and he is subtracting the non-snowy ones. In that way he is getting the difference. That is the main difference which we have to reach, which has to be on the right hand side of our expression. That thing is basically this diff. Then comes this f, which is I think the first array that we formed. uh, okay, let us see. F is being declared over here. Okay, yeah, S is being used. So it is basically that thing which we have done over here. Uh, some so from the F array, from this array only, he is calculating directly this sum thing. So similar kind of a strategy. Let me check once. What we did, sum of ij is that is correct. So we are finding the sum from there, that sum of the range. And what he has done is slightly different maybe. He has said that f of ij, this basically means that up to there, this is basically our sum ij. So he says that I think this may be helpful for us. Yes, we are taking the previous thing and the above thing, but we are not considering the current element. I think we are left. We have So here we have to add the current element. So f of, or what array is given? That thing, the snowy thing, snowy ij. If that is equal to 1, then we are going to take a 1, otherwise a -1, something like this. Yeah. So then this will give the summation up to any place, and then we will use that in our sum ijk. So we are not adding the current element. That was a problem. I mean, everywhere, wherever you are applying this kind of a technique, you have to apply the current element. So yeah, this is the correct expression which he has used. He is using exactly the same thing, Fij. And then next step, he is doing something that we have done, which is I plus k, j plus k minus, I mean, we have done ij and I minus k, j minus k thing. He is doing ij and I plus k, j plus k thing. The same kind of a thing. And then he's finding the GCD with the existing GCD. He's finding the GCD of all of them. And then he's checking whether our difference is divisible by the GCD or not. I think he could have left this as a subset of that only. 0 modulus GCD will be equal to 0. I think he's checking whether this G is equal to 0 or not. If G is equal to 0, then diff has to be equal to 0. Otherwise, G is greater than 0 and diff modulus G is equal to 0. That is correct. So yeah, correct. So yeah, that's the right code. So we have discussed 4 problems here. As you saw, there was a good blend of mathematics, data structures, and algorithms. You can see the kind of recurrences we did in dynamic programming, and we used binary search to find out the answers faster, to explore our subproblems faster. And in the last problem, it was more about uh, looking at what your objective is, and then looking at what informations you have, and then what decides the yes no. I think there you needed some mathematics to understand what decides that yes no. It's a linear combination. So that's a mathematical thing. Our problems A and B were largely intuitive, but problem B was rather about do the steps, make it fast wherever you can make it fast, and the multiplicative divisive things, yeah, basically make those as benchmarks, those as the milestones. Reach over there, do the additions fast, and then at the divisions and all, take the time. So in that way, we reached some optimal approaches. I hope you found the session interesting. If you have watched, if you have attended the contest, then I hope you found these approaches helpful. And if you have not attended the contest, if you did not participate in the contest, I would encourage you to please solve yourself. And then if you, and then basically compare against the approaches that I have used over here. And you can look at the CACS problem set, where I have shared some insights about how to solve similar DP problems. I'll be sharing more. I'll be sharing more videos related to that. Till then, take care, keep coding. See you all in upcoming contests. I want you to practice more and solve contests much more. And also, yeah, keep practicing. See you all. Bye.